transforming trig functions. There's a lot of info. We'll talk about this. So this here, sine x, this is a function. And you guys will have done like function notation before, f at x is equal to, and we write something out. We say it's equal to something, and we usually make it up because f is a bit arbitrary. This is also a function. It actually has the argument. So in our function notation, this is known as the argument. Okay, and that's what we put into this function, and then we carry out a bunch of calculations, and it gives us an answer. That's exactly what sine is. Sine is some function. There's actually some underlying mathematics. It's actually a series of calculations, an infinite series of stuff. And we plug in this argument, x, whatever it is, and our calculator carries this out. It turns out that if we carry this, if we continuously plug into this function with an ever increasing x, so we take like our x value and we just keep increasing it. So, you know, you go from 0 and from 1, 2, I shouldn't even do that. Those are integers. Technically, you can use even real numbers here. But you can go 0 all the way to infinity. It's probably a better example. We can represent this on a graph over a long period of time. And it so turns out that this is called a periodic relationship, which means it's a repetitive relationship. So it has some kind of relationship that goes like this. Doing the best I can to keep this. Yeah, that looks close. It has this repetitive relationship, and if we go backwards, it does the exact same thing too. Okay. This is known, if it is sine x, okay, this is known as the parent function. They call it a parent function because it's the like standard function that we make all of our references from. So if something has been stretched or compressed or shifted, we mean from this place. Okay, so this is our original, so it's like our starting point. And we can bring up our graphing calculator. We'll go to that one in a second there. I can type it in, sine x. Hey, now this is in radians, which you guys are probably not used to using, are you? You guys use radians? No, don't worry about that concept. And I'm going to change it to degrees for now, and it's going to look more like this. Whoops, that's the wrong axis I was manipulating. I want this one to be like that. There we go. Okay. Let's change this a bit. Let's change this to, I don't know, 3 and -3. And make this, let's go to 500. There we go. That's a little more wave-like. It's all the same, but this is what we mean by a periodic function. And a key part of this is there's 5 key points in one period. So a period in this case is when we return to the same point along this wave in the same fashion. So you may notice, like, for instance, if I start at 0, I actually return to 0 after 180 degrees, or when my x value is 180, but not in the same fashion. Here, it's on a decreasing slope, while here, my rate of change is increasing. So it's not in the same fashion have I repeated or returned. So I actually have to come up and, here we go. We're getting that same fashion. Another way to look at this would maybe just the peaks. You can look at this peak and this peak, and we just take the difference between our x values. So 450 subtract 90 ends up being 360. But if we know our parent function well enough of sine x, we know that these are 5 really key points, and they'll help us graph it. If we keep these points, we just fit a bit of a curve between the points. We can graph this relatively easily and repeat it from there. In fact, what I'm going to do is I'm going to turn it into a table. Those aren't wonderful, but I'm going to change these values. Let's make that 0, this one 90, 180, 270, and 360. There we go. So we got our key points there on the graph. What we also want to do is we want to relate how to stretch and compress a graph like this. So I'm going to jump back over. We've kind of shown you the graph. We'll jump back to this information. It turns out that no matter what my function is, I can apply specific variables to the function. So let's say they call this the general equation for transformations. So it might say our f at x of our function is equal to a. Okay, now this part with the letter f might get a little confusing. And we have b minus c. And now your class or teacher might use different letters, but the position in relation to the original function, my f looks ridiculous. I don't know if you'll even be able to tell it's enough. I'm going to change that. This is the general equation for transformations. F means I can put any function I want into that. And this, the course you're in is called functions at the moment. So instead of f, in our case, remember I told you sine is a function?
Yeah.
I'm going to put sine in there. So we're going to say our function is, so I'll say f at x is equal to sine. And I'm going to rewrite everything out. A, I have this bracket here. Now, your course, they may not talk about the b being the horizontal stretches and compressions. They may, I'm not 100% sure. Sometimes they leave the b out. It's a little trickier to deal with. And plus d. And what's important here is what I want you to notice is that I've taken this function, I've replaced it with a new function, it has a specific wave to it or shape to it. So it's this general wave function. And then depending on what value I put in for these variables, it manipulates and transforms this parent function. Okay? So we're going to talk about what each of them do because each of these is going to be pretty important to transformations. A does something called a vertical stretch. So I say it goes up and down. And it shouldn't just say stretch, it can also do a compression. So maybe I'll write it out. Vertical stretch or compression. It just depends on the value of A. Okay, so I'll say it goes up and down. And if A is greater than 1, we get a stretch. And if A is less than 1 but greater than 0, we get a compression. So think of like an elastic band being pulled up or down. So think of this being pulled this way, and a compression is like the opposite. It's being squished inwards, okay? B is a horizontal stretch or compression. So it means we're going left to right. And in this case, if B is greater than 1, we actually get a horizontal compression. So in other words, it's like getting squished from both sides. And if B is less than 1 but greater than 0, we get a horizontal stretch, which is like taking this and pulling it on these two ends. So the arrow's telling you which direction to go, left and right. Okay? So that would be B. This would be A. Those ones are a little hard to visualize, and we'll show you with the graphing software what they look like. C and D are a bit easier. C is a, let's say, horizontal shift. And it depends on the value of C. So this negative gets a little tricky here. So I'm actually going to fill this part out second. We're going to jump right over to vertical shift, which is our D value. And it goes up and down. And if D is positive, it goes up. And if D is negative, I'll go like this, it goes down. Okay. This one's a little trickier. The actual values of C are the same as this. But the problem is there's a negative in front of it. So if I put in positive 5 here, well, plus 5 is just plus 5. And if I have a negative 5, plus negative 5 is just negative 5. So it looks the way you would think it would look. Because this is negative here, if you remember like your integer rules, if C is, I'm going to say equal to negative 2, and I go put it into x minus 2, you might have remembered this from quadratics. This becomes x plus 2. So it has this relationship where it looks like it's a positive 2, but it gets shifted to the left. Do you remember that with quadratics at all? This is the exact same concept. In fact, this is the exact same placement. This is the same idea as a general equation for a function. I can apply this to quadratics, sine functions. You're going to learn in your next course, you can apply this general transformation equation to all different types of functions. For the sake of the argument, I'm going to say that horizontal, left and right, and we're just going to write it this way. Hopefully it doesn't get confusing. If it looks like, we'll include, see how I put the green with the negative there? If it looks like C is a negative, we're going to say it's going to move to the right. And if it looks like C is a positive, we're going to move it to the left. Okay, just remember that technically that's not true. It's because that negative's there, but this is the idea of it. Okay, so this tells us how to shift something from the original equation, which was that parent function of sine. So let's go back to our graphing software, and we're going to apply some of these ideas. So for instance, I'm going to give myself an A here. Got my slider A. A is currently 1. I said if I move A, and you know what I'm going to do? I'm going to have one just above it. And we'll make this one black so it's easier to see. Here we go. As I move A, give myself step 2, -1. Okay. If you notice, when I'm on 1, it looks like the original function, which is right. As soon as the A value goes up, it looks like the peak and the trough are being pulled from the top and bottom. Okay, and then as I shrink it, it comes back down. And then when I'm less than 1, it looks like the peak and trough are being squished. Now, eventually, we get a flip. That's when I get into my negative values. Now, notice as the negative value gets larger, it looks like it's being pulled. And as the negative value is decreasing, it looks like it's getting flatter. Okay?
Yeah.
So this is called your vertical stretch or compression. Quadratics work the exact same with this A value. The value that's newer to you, because we don't really use it within the quadratic because it just gets kind of factored into, it looks like a vertical stretch and compression when we do it, but you'll be able to see it with the sign much easier, is this concept of B. Okay, my B value. As B gets larger, if you remember, it looks like the wave, well, this is really taken off. I'm going to make it a little smaller so it's easier to tell. Okay. It looks like the wave's being crushed from the outside inwards. Okay, so we'll go at the beginning here. So as it's getting larger and larger, it looks like it's getting squished more and more from the side. So it looks like it's being compressed. And then as it gets smaller, it looks like it's being pulled outwards. And then eventually we get a flip on that axis. And then same idea, as it gets larger, it looks like it's being compressed from the outside. And then as it gets smaller, so it goes back and forth. This is the idea of a horizontal stretch and compression. Does that idea make sense? So that was your B value, and that was your A value. The other two that are probably going to be easier to look at, interference, period of amplitude. Did I lose one? Oh. Does this one give it to me? No, that's our amplitude. That's our period. Oh, that was my decimals and it died on me. Oh, that's too bad. Okay, we'll make it. The other two that are a little easier to look at are sine x plus, I'm going to call this letter D, and we'll make a slider here. This is a shift. So as that D value goes up, you can see this object just moves up and down. Nothing really changes to its general shape. It just has any of the points are all pulled upwards or they're all pulled downwards. And then the same idea happens here. Sine x minus c, we said. We get our slider here. Now this one's where it gets a little counterintuitive. Oh, it's because it's in degrees. That's why I'm like, this is such a small shift. Let's go to 90 and -90. There we go. You start to see it moving just to the right or just to the left. So that's how these letters all manipulate this wave. This is generally what you guys are going to be working with. Trying to manipulate the parent function, and you're going to end up putting in values to make it shift to the right or the left, up or down, horizontally compress or vertically stretch, and then flip things around. So this is the general idea of what you guys are trying to work with. We can make some questions about it. The one other piece I wouldn't mind showing you is just the one here. It is our period and our amplitude change with these things. So this is an A value. You can see it's in front of a cos function, which is really similar to a sine one. It just kind of starts at a different place. Sine started at the origin, cos starts up here. If I increase my A value, can I say I want it to go by? Yeah, really slow. If I increase my A value, do you see how the amplitude is changing? The amplitude is the distance from here to the peak. How much farther? There we go, goes up. So that's that purple line there. That's currently the amplitude. So as we vertically stretch it, the amplitude is growing or shrinking, depending what we do. So that A value gets down. Eventually, we're going to flip, and then the amplitude's just going in the opposite direction. Okay, pull this one back up. B, okay, is this idea here. This is a horizontal compression. And you'll see this is the period. It's the distance between these two peaks. See how it squishes together? It flips around the other way. But our period is constantly changing as we horizontally compress or stretch our original function here. So just be aware that depending on a vertical stretch or a horizontal stretch, that changes the amplitude and the period of the function. Okay?